Now that we have a basic understanding of graph neural network and the foundation model, we will share the graph prompt to explain how should we decide graph neural network prompt tuning. The key point here is that we need to design a prompt similar to GPT, so that it can be used for model pretrain and can switch to different downstream tasks from the prompt. Here are three research motivations, which are also three challenges that need to be addressed. The first one is both pre-trained models and the fine-tuned models require a large amount of label data. The second is this is an inconsistent objective of the pre-trained model and the downstream task. The third motivation is different tasks have different focal points. How should we decide a prompt to switch between different tasks? This is overall of the research. First, how can we unify node classification and the graph classification? Defining a cat-hop egg node for the target node, then assign the node label to the graph label. Now we have a unified framework that can handle both node classification and the graph classification problem. In this paper, our readout function uses some pooling. So we randomly select a node from the graph, then randomly select one of its neighboring nodes. Also, it's also randomly select a node that is not close to it for contrastive learning. In this study, we use cosine similarity for the calculations. For neighboring nodes, we aim for their similarity to approach 1, and for non-neighboring nodes, we aim to their similarity to approach -1. This self-supervised learning method is used to train the graph neural network encoder. Next, we moving on the prompt training part. After obtaining the output from the graph neural network encoder, we get a prompt value that match the size of the encoder output. Then we perform elements-wise multiplication of these two values. In this process, we select k samples from each category. For example, if we take two categories with 3 samples for each, we input 3 labeled graph data and compute the average for these 3 samples. Then we input a unlabeled sample for calculate its similarity with each category based on the output. We assign the label of the most similar category to the unlabeled sample. Next, we feed the graph neural network encoder parameter and calculate the similarity for this data to train our prompt parameter. We conducted experiments on 5 datasets for GraphPrompt. We can see that in node classification, our method outperforms other classic methods with just a small amount of data. In the protein experience, the graph shows the relationship between k-sharp and the accuracy indicates that for k-sharp value below 8, GraphPrompt achieves higher accuracy than other methods. In the enzyme experiment, including those below 10, GraphPrompt consistently achieved higher accuracy than other methods. Moving on to our summary. So the innovation of this paper lies in its design of a unified framework for both node classification and the graph classification. For different downstream tasks, it uses a learnable prompt to switch between different tasks. In terms of soundness, the paper provides a sufficient theoretical foundation and references 5 benchmarks for experimental validation. Finally, it compares the graph prompt with state-of-the-art method. Regarding significance, we can see that the graph prompt is highly effective in few-shot learning and it's using prompts to switch between different tasks. Lastly, in the graph, we observe the that as the number of shots increases, other methods may surpass it. This leads us to consider whether GraphPrompt can be combined with scenarios involving data imbalances to further enhance its advantage. Finally, we have two questions for the author. The first one is, how does the math perform when dealing with the large-scale graphs? The second is, how does it compare with other graph neural network methods that use prompt